In this discussion, I'd like to talk about infinite series, which loosely speaking involves adding things up, except that the number of things we're going to add up is unlimited or infinite, as opposed to the way we usually do stuff in algebra and calculus. So we're going to start off with a sequence, A1, A2, A3, and so on. Parenthetically, sometimes it's convenient to start indexing at 0. That's just a matter of convenience, though. For now, I'll assume that my indexing starts at 1. And given this sequence, A1, A2, and so on, we're going to create a new sequence that's based on it. We'll call this new sequence name capital S. So we'll have S1, S2, S3, and so on. And we need to figure out how exactly we're going to build this new sequence. S number 1 is just going to be A1. S number 2 is A1 plus A2. S number 3 is A1 plus A2 plus A3, and so on and so forth. If k is a positive integer, then S number k is going to be A1 plus A2, and continue adding until you've added a number k in. If you remember from our discussion of integration, we can write that as a summation symbol if we want to be all fancy looking about it. These capital S numbers form a sequence. Like any other sequence, that sequence of S numbers either converges or it doesn't. If it does, I'm going to call the real number that it converges to capital S. And not to keep hammering on this, real numbers are not the infinity symbol or negative infinity. If that happens, then what we're going to do is we're going to say that the sum n equal 1 to infinity, a sub n, is equal to this S. We'll call the sum an infinite series. We'll say that it converges to S if this happens. So the value of the infinite series is the limit of these S numbers, which we'll call partial sums for obvious reasons. They're the sum that we're really interested in, except they don't include all the terms we're interested in. And we'll say that all three of these things are the thing the series converges to, which I'll symbolize by the letter capital S with no index on it. Now, if that doesn't happen, that means that the limit of the SK numbers doesn't exist. If that happens, regardless of the details of how that limit fails to exist, we'll say that the infinite series diverges, fails to converge, doesn't exist, and so on. There are several ways that this could happen. It could be that the partial sums become big and arbitrarily positive as you allow the index to increase. It could be that the partial sums tend to infinity. The partial sums could also tend to negative infinity. Another thing that could happen is that the partial sums are bounded, but even so, they don't settle down to any particular actual real number. If any of these things happen, we'll say that the infinite series diverges. There's a huge number of topics involving infinite series. Here today, I want to think about only 3 of them. I want to think about geometric series, I want to think about telescoping series, and I want to think about the situation involving the general nth term of a series, what that can tell us and what it fails to tell us. For the first one, the geometric series, I'm going to say that I have 2 numbers, a and r. These are constants. I'm going to build up a sequence of partial sums. For this particular instance, it's more convenient for me to start indexing at 0. So this is what we'll do. We're going to define S0 to just be the constant A. S1 is going to be A plus A times R. S2 is going to be A plus A times R plus A times R squared. The third one is A plus AR plus AR squared plus AR cubed. It's obvious why I wanted to start indexing at 0. The index on the partial sum will match the highest power of the R that shows up in the partial sum, so it's easier to remember. This R number is called the common ratio. As I move from one partial sum to the next one, I take the biggest power of R term, which would just be the A here, and multiply it by R. Then I do the same thing to get AR squared and AR cubed and so on. So in one of these geometric series that we're going to look at, each term is R times the previous term. But if I tell you the A and the R, for which A's and R's does this series converge? And if I can figure out that it does converge, can I figure out what it converges to? Oh, and a comment, I may as well assume that A is not 0, because if A is 0, then this is 0, those are 0, those are 0, those are 0. If the A is not 0, my infinite series obviously converges to 0, and nothing interesting happens. So only A being different from 0 is interesting here. If I write out a partial sum, if I write out S number K, it's going to be A plus AR, and I'm going to continue adding terms until I get out to the A times R to the K power term. Now, once again, this only has a finite number of terms in it. This is something that a person who knows college algebra would be comfortable with. I'm going to take SK and I'm going to multiply it by R. I can use the distributive law to do that. Every term in SK is going to have its power of R increased by 1 when I do this. A times R, AR times R, AR squared times R, and at the very end, I'll have A times R to the K power times R, which will be A times R to the K plus 1 power. A comment that's going to help me in a minute. Right before this last term, the term before it is going to have 1 power of R less. The term before this one is going to be A times R to the K power. So fix that fact in your mind. Write out S sub K again. When I write out the R times SK, I'm going to shift the terms a little to the right to make it more obvious what I'm doing. R times SK is this, and the term right before that was A times R to the K. So write out all of those terms. The last one is A times R to the K plus 1, and the one before that was A times R to the K. It should be obvious to everybody why I'm doing this. I'm going to take this second line and I'm going to subtract it away from this first one. I'll have SK minus R times SK, which is 1 minus R times SK. The A times R's cancel out. The A times R squares cancel out. The A times R to the K's cancel out. The only thing that ends up not canceling out is this A minus this A raised to the A times R to the K plus 1 power, that is. And again, these are finite sums, no infinite series or anything, so I feel comfortable doing this. We'll have to look at the case where R equals 1 separately. But for right now, I'm going to assume that's not what we're looking at. We have an R that isn't equal to 1. So in the preceding formula, I can divide through by 1 minus R and find out that partial sum number K is A over 1 minus R minus A over 1 minus R times R raised to the K plus 1 power. What we're wanting to do is to take the limit of these partial sums as the index tends to infinity. So I want to look at the limit as K tends to infinity of partial sum number K, which we have figured out a literal formula for. Now, looking at this, there's some parts that don't bother me and some parts that do. A over 1 minus R has no K in it. So A over 1 minus R, in terms of taking this limit, is a constant. I've got a constant minus a constant times R to the K plus 1 power. The A over 1 minus R has no say in whether this limit exists or not. The only thing that's going to matter is the part that depends on the K, so that's what we've got to think about. If you think about this though, if absolute value of R is bigger than 1, so maybe R is 6, absolute value of that would be 6. I would be looking at K plus first powers of 6. As K tends to infinity, that's going to blow up on me. So if the absolute value of R is bigger than 1, this whole thing is going to diverge. If R is less than 1 in absolute value, like R equals a half, for instance, I would be taking powers of 1/2, like 1/2 squared and 1/2 cubed and 1/2 to the 4th power and so on. R to the K plus 1 is going to tend to 0 in that case. Also, if R were negative 1/3, the same thing would happen. If R is equal to 1 in absolute value, that is R equal 1 or R equal negative 1, we don't know about those directly. We'll have to figure out what happens for those in a separate calculation. For now, we're only going to look at the case where absolute value of R is less than 1. I take the limit of the partial sums, which is the limit of the formula that we figured out for the partial sums. This is a constant, so I'll write it down, minus A over 1 minus R is a constant, times, if R is smaller than 1 in absolute value, and I take powers of R, as the power increases, those powers get very close to 0. So my limit is going to be A over 1 minus R minus A over 1 minus R times 0. This whole second piece goes away. In the special case where absolute R is less than 1, the infinite series of this type, which we'll call geometric series, converges. Not only does it converge, I can actually tell you what it converges to as well. It converges to A over 1 minus R. For a specific example, suppose that A was 3 and R was a half. We can write out a few of the partial sums to see what we're looking at here, but the important feature is that the R is a half. Absolute value of r is absolute value of 1/2, which is 1/2, which is less than 1. I know this infinite series converges now. Not only do I know that it converges, I know that it converges to a over 1 minus r. The a, the initial term, was 3. I have to write down 1 minus r, 1 minus a half, which is a half. 3 divided by a half is 6. If you look at the infinite sum, sum I equals 0 to infinity, 3 times 1/2 raised to the I power, which is the sum of an infinite number of positive terms, it turns out that that adds up to a nice finite sum, namely 6. Another example, the sum I equals 0 to infinity of 5 multiplied by the ith power of 7/8. Obviously, the a is 5 and the r is 7/8. Absolute value of r is less than 1, so I automatically know this series converges. And the thing it converges to is a over 1 minus r, which, if you do just a little bit of arithmetic, turns out to be 40. There's no need for either a or r to be positive, though. You could have a situation where a was 6 and r was negative 1/3. Your partial sums, the first few of which would be 6 and 6 minus 6 times 1/3. I'm not going to bother simplifying that. 6 plus 6 times negative 1/3 plus 6 times the square of negative 1/3, and so on and so forth. The absolute value of r is absolute of negative 1/3, which is 1/3, which is less than 1. I already know the infinite series converges. On the next page, we'll figure out the number that it converges to. It converges to a over 1 minus r, which is 6 over 1 minus negative 1/3. And then you do the arithmetic, and it turns out that the infinite series converges to 4.5. What if the absolute value of r is bigger than 1? As an example, the sum I equals 0 to infinity of 2 times 3 raised to the I power. If you look at the partial sums, you see what's going to go on here. The initial term is 2, then you'll have 2 plus 2 times 3 to the 1 power, 2 plus 6. The next one will be 2 plus 6 plus 2 times 3 squared, 2 plus 6 plus 18. All of these partial sums are positive, they're getting bigger, and even worse, each one of them is bigger than the last term, which is 2 times 3 raised to the k power. Obviously, these are not going to settle down to anything. If you wanted to write this as a limit thing, you could say that the infinite series equals plus infinity, but by now you can see why I don't like talking like that. It's worth mentioning that you could make a mistake here. If you sat down and looked at this series and said to yourself, everything's fine, a is 2 and r is 3. If you had memorized a formula and not thought about what's going on, if you didn't know any better, you would say, everything's fine. The infinite series adds up to a over 1 minus r. That would be 2 divided by 1 minus 3. That would be 2 divided by negative 2, which would be negative 1. Hopefully nobody will fall for that. How can you add up positive numbers and end up with a negative number for an answer? Answer, you can't. That formula, the a over 1 minus r thing, only works when absolute value of r is less than 1, and that's not the case here. This should remind you of that improper integral where you were supposed to get a positive answer and ended up with some negative answer instead. You can't use a formula in a context where it doesn't apply. What if r was 1? As we said previously, if a were 0, we're just talking nonsense. We don't actually have an infinite series. So I'll just make up a non-zero number for a. I'll say that a is 2 and r is 1. So S0 is 2, S1 is 2 plus 2 times r to the 1 power, but 1 to the 1 power is just 1. So this is 2 plus 2. S number 2 is 2 plus 2 times 1 to the 1 power plus 2 times 1 to the 2 power, which will be 2 plus 2 plus 2. And I think it's pretty obvious that as you continue doing this, the partial sums will become as big as you would care to make them. So most people would just write that the limit is plus infinity. Or if you want to be picky about it, this infinite series diverges, does not converge, does not exist. That is to say, it equals plus infinity. Usual comment. If r is equal to -1, this is also no good, but it's no good in a different way than the previous one was. Let's say that a is 3 and r is -1. S0 will be 3. S1 will be 3 plus 3 times r raised to the first power, which is 0. S number 2, you have those same terms as before, but you also have plus 3 times -1 squared. That ends up giving you 3. S number 3, after you grind through the arithmetic, ends up giving you 0 back for an answer. The partial sums are 3, 0, 3, 0, 3, 0, 3, 0, and so on. The limit does not exist because that collection of numbers doesn't settle down to some particular number. The limit doesn't exist, but if you say equals plus infinity, that's wrong because that's not what's going on here. The limit doesn't exist because I get finite numbers for my partial sums always, and they oscillate back and forth between 3 and 0. There's a certain category of series in which you can rearrange things. So I want to look next at least one example of these telescoping series. I'm going to have the sum n equal 1 to infinity, 3 divided by n times n plus 3. This is not geometric, so I can't use any of those ideas. So I'm going to try something else. Like we were doing back in the methods of integration stuff, I'm going to try to use partial fractions to rewrite the things that I'm adding up. Since the denominator's already been factored, we'll just say we're going to try to write 3 over n times n plus 3 as a constant divided by n plus another constant divided by n plus 3. The manipulations that we're going to use are exactly the same as we did in partial fractions. Multiply through by n times n plus 3, and you get the basic equation, as your textbook calls it. There are two numbers that you should never stick into this equation, 0 and -3. So naturally, that's what we'll do. Remember, there was a continuity argument to do with that. If n is 0, the term with the b in it goes away, and I get 3 equals 3 times a. which tells me a is 1. If you let n equal -3, the term with the a in it goes away, and this says that 3 equals -3 times b, which tells me that b is -1. So I can split this quantity up into 1 over n minus 1 over n plus 3. If you want to do a sanity check, start with this, write it as a single fraction, and you'll see that after you get done simplifying it, you do get back what you're supposed to get. Now, this means my infinite series is exactly the same thing as this. If I can figure out some way of dealing with that, we'll be in business. Now, infinite series are limits, which means we have to be really careful about how we manipulate them. On the other hand, these partial sums are just sums of finite number of terms, which means everything that you think should be true in college algebra is true. I'm going to add up the sum n equal 1 to infinity, n equal 1 to k, that is here, of 1 over n minus 1 over n plus 3. Finite number of terms, I can split that up into these two terms separately, and there's absolutely no ambiguity about the thing. I'm going to write out some terms for each one of these. I'm looking at partial sum number k. The sum n equal 1 to k 1 over n is literally 1 over 1 plus 1 over 2 plus, and then you stop at 1 over k. This is slightly trickier. I'm going to have 1 over 1 plus 3, 1 over 2 plus 3, and when the index is k, the very last one will be 1 over k plus 3. I need to make a couple of comments about what terms go where so I can see what I'm doing. Right before 1 over k plus 3 is 1 over k plus 2. Right before that one is 1 over k plus 1. And right before that one is 1 over k. And there's a 1 over k here. So this should be enough to let me see what I'm doing. Now, a purist would object and say that k has to be at least 5 for what I'm about to do to make sense, but that's not really a problem because we're going to take the limit as k tends to infinity anyway, so really that's a non-issue. If you write all this stuff out, some interesting things happen. The 1/4ths are going to cancel each other out when I subtract. Also the 1/5ths, and so on and so forth. The 1 over k's are going to cancel each other out as well, but there's some stuff that doesn't cancel out. In here, I'm never subtracting away 1 over 1 or 1 over 2 or 1 over 3, so those stay. There is no 1 over k plus 1 or 1 over k plus 2 or 1 over k plus 3 in this part, so those hang around also. If you add up the fractions, if I've done my arithmetic correctly, that's 11/6. S number k is 11/6 minus 1 over k plus 1 minus 1 over k plus 2 minus 1 over k plus 3. Sk is a constant with 3 things subtracted away from it, not an infinite number of things, just 3 things. If you take the limit as k tends to infinity of S number k, that's a constant, so its limit is 11/6, and each one of these 3 things tends to 0 as k tends to infinity. So the limit of the partial sums is 11/6 minus 0 minus 0 minus 0, which is 11/6. The sum, n equal 1 to infinity, 3 over n times n plus 3 is 11/6. This is an example of what we mean by a telescoping series. They call it that after the children's toy telescopes they used to sell, where at the end of your viewing, you would push on both ends and lots of stuff in the middle would fold together. Lots of stuff here cancels out. So this is the reason people call it by this name. There's a useful result concerning the general nth term of a series, which I want to talk about right now. It's an if something happens, then I guarantee you that something else happens type of thing. It's a logic thing. Suppose you have an infinite series. If that infinite series converges, then I guarantee you something. I guarantee you that the individual terms tend to 0. Why? If this series converges, then the limit of the partial sums must be some particular number, which I'll call S. What that means is, if I make the index on a partial sum really big, I can make the partial sum look as much like S as I want. The limit of any partial sums whose indexes are tending to infinity would be S. But see, A sub n is A1 plus A2 out to AN minus A1 plus A2 out to a number n minus 1. This is a partial sum. This is another partial sum. As n tends to infinity, this partial sum has to have limit S, and the limit of this partial sum, if you think about it, as n tends to infinity, n minus 1 also has to tend to infinity. The limit of this quantity, as n tends to infinity, is also S, and S minus S is 0. If you've got a series that converges, I guarantee you the individual terms must tend to 0. It's impossible for anything else to happen. A little bit of logic. Suppose that P and Q are statements that something happens. If you've got a relation that says if P, then Q, which more generally means if P is true, then Q is true. That kind of thing is called a conditional statement. If you take math reasoning, you'll find out more about this sort of stuff that you probably want to know. But there is another conditional that you could cook up that says if Q is not true, if Q is false, then P is not true, P is false. This is called the logical contrapositive of if P, then Q. It turns out, as you'll find out in math reasoning maybe, these two statements are logically equivalent to each other. If the first one is true, the second one is true. If the first one is false, the second one is false, and vice versa. We have just figured out that if an infinite series converges, then the limit of its individual terms is 0. The contrapositive of that is if this is not true, then that is not true. So if the limit as n tends to infinity of an is not 0, including the cases where the limit doesn't even exist, if the limit isn't 0, then the infinite series diverges. So one of the first things you think about when you look at an infinite series that you're not familiar with, you look at its terms and you see if the individual terms tend to zero or not. If they don't, then you know something. If they don't, you know the series diverges. So these two statements are absolutely reliable. If the premise, the if part, in one of them is true, the conclusion, the then part, is also true. Absolutely guaranteed under all circumstances. How about this? If the limit as n tends to infinity of an is 0, what if the individual terms tend to 0? Then the infinite series converges. I'm just going to tell you before we look at examples, this is not a reliable statement. You cannot rely on the individual terms being 0 to guarantee that the series converges. It's too bad, but it doesn't work that way. Firstly, think of the sum we were looking at a little bit ago. The sum n equals 1 to infinity, 3 over n times n plus 3. Obviously, the limit of the individual terms is 0. Also, we had to work at it a little bit, but it turned out that the series converged on us. If I didn't know any better, I would take this as meaning whenever the individual terms go to 0, the series converges, but unfortunately, it's not true. You want to think about the series sum n equal 1 to infinity, 1 over n. The individual terms, the 1 over n, tend to 0 as n tends to infinity. That makes us hope that the series with the 1 over n in it converges. Turns out that it's a false hope, though. Oh, by the way, the name of this series is the Harmonic Series for historical reasons. I want to think about taking a segment out of the bunch of numbers that we're adding up, and I'm just going to think about it. I'm going to start at 1 over k. K is some positive integer. I'm going to add the next term, 1 over k plus 1, the next one, 1 over k plus 2, and I'm going to go all the way out until I'm adding 1 over k plus k. Which of course means I'm going to be adding 1 over k, 1 over k plus 1, 1 over k plus 2, until I get out to 1 over 2k. I have doubled the number on the denominator from where I started. I want to think about two things here. How many of these terms are there, and how big are they? If I think about what I'm adding to the k on the bottom, I would have 1, 2, so on and so forth, k. There are k of these terms. And then I've got that one, which makes k plus 1. We are adding up k plus 1 terms here. On the other hand, say k was 5 or something. 1 over 5 plus 1 over 6 plus 1 over 7, 1 over 8, 1 over 9, 1 over 10, which is 2 times 5. The biggest number is the first one. The next biggest one is the next one. The one at the end is the smallest one. So I'm going to be adding up k plus 1 numbers. Each one of those numbers is at least that big, is at least 1 over 2 times k. So 1 over k plus out to 1 over 2k. I'm adding up k plus 1 things, each one of which is at least 1 over 2k. This sum has to be at least k plus 1 times the smallest one of these numbers I'm adding up has to be at least k plus 1 times 1 over 2k, which is bigger than k times 1 over 2 times k, which is a half. So if I take a segment out of this harmonic series, I pick a number k and I calculate 1 over k plus 1 over k plus 1 and keep going until I've doubled the original number on the bottom. Regardless of where I started, which k I started at, that segment by itself adds up to at least a half. This seems innocent enough at first, but it's the formula of doom for the harmonic series. S2 is silly to look at, but I'll write it down anyhow. S2 is 1 over 1 plus 1 over 2. What we've just figured out is that's at least a half, which is silly because it's actually equal to 3 halves, which is obviously bigger than a half. But much less obviously, look at S number 6. 1 over 1 plus 1 over 2, the next term that you would add in would be 1 over 3. If you double 3, you get 6. So this is one of these double the index deals. And 1 over 3 out to 1 over 6 is another one. If I want to do what I think I want to do, I'll have a doubling thing here, another doubling thing here. The next term in the series after the 1, 6 would be plus 1 over 7. And I want to add in enough terms so that I've doubled the number on the bottom of the fraction. I'll add in 1 over 7 out to 1 over 14, and that would give me sequence member number 14 of the partial sums. The next term after 1 over 14 would be 1 over 15, and I want to add up enough terms until I've doubled the 15 on the bottom. So I'll add in 1 over 15 out to 1 over 30, which means I'm looking at S number 30. It should be obvious to everybody that I could continue doing this as long as I want to. So if I go back and look at that previous series, we've seen that we can use partial fractions to split it up into 1 over n minus 1 over n plus 3. That's completely valid because you can algebraically check that 1 over n minus 1 over n plus 3 is what it's supposed to be. But splitting it up into the difference of two sums is invalid, completely invalid, incorrect, wrong, not good, because we just saw a minute ago that infinite series diverges, and this infinite series diverges also. And it's only legal to split limits up like this, which is what these infinite series are, when both of them exist as actual, honest to goodness, real numbers, which doesn't happen for either one of those two things. This is totally invalid. But if we press on, having figured out that both of those sums are uh, equal to infinity, if you didn't realize that the infinity symbol isn't a number, you would write this as infinity minus infinity, which is totally invalid because infinity isn't a number, and you can't feed things that are not numbers through the subtraction process. On the other hand, we showed previously by thinking about it that that infinite series actually exists. It converges. Its value is 11 divided by 6. So once again, if you think infinity is a number, you have to come to the conclusion that infinity minus infinity is 11 over 6, which hopefully by now doesn't do anything except make you kind of laugh at it because it's obviously wrong. There is a vast array of infinite series that we can look at, and we've looked at in this discussion geometric series, telescoping series, and we've investigated the nth term business a little bit here. I think I'm going to call that enough for today. Tomorrow, we're going to talk about the integral test, which is a procedure by which you can sometimes determine whether or not an infinite series converges or diverges by using improper integrals.